Hey guys, this is Mr. Ainsworth, and we're going to get into the homework problems over the shell method on lesson 18. And just keep in mind that even though I'm going to solve these with the shell method, you could always back them up with other methods like the disc or washer method. So, pay attention to that. In fact, that's a great way to review is, solve a problem using the shell method and then use the disc or washer method to check your answers. All right. So keep that in mind. It's a great idea. If you can solve a problem using like 3 different methods or at least 2 different methods that back each other up, hey, that means you know what you're doing. And not only that, you know the different techniques that are used and displayed in the lessons here. So keep that in mind, and also learn how to do with the calculator. The solutions are provided here in approximation form. They're to the nearest thousands. And I'm going to do, at most times, or throughout the lesson, I'm going to solve them in exact form too, and then show you how to use it on the calculator and do it with the function integration on the 84. Okay? So the first thing we want to do is got to set up the boundary region and then revolve it about the y-axis in this case. So keep that in mind. We're going to revolve around the y-axis in the first case. So let's graph. In fact, you know what? Also, make a note. You can change the scale and the axes as you need to. Okay, let me write that down. So change scale on axes as you need to. So remember that. I just put these graphs in just to help us with the graphing. But many times we're going to change the scale. Okay, so since I'm talking about changing the scale, let's go for it here, and let's enlarge this diagram here so we can see it, because my scale here is quite small. But disregard the numbers, okay? Let's just change the scale, and let's set this to 1, 2, 3, 4, and again 1, 2, 3, and let's change the scale, and so we can blow this up a little bit. All right, let's graph y equals x first. Has a slope of 1 going through the origin. Let me change the color of that. Okay. All right, let's try that one more time. So we've got y equals x going through the origin here. So graph that line here. X equals 2 is a vertical line at x equals 2. And y equals 0 is the horizontal line, basically the y-axis there. So again, here's y equals 0. Here's x equals 2. Here's y equals x. You need to be able to graph that really quickly there. And then bound the region by all 3 functions. That's this area right here between 0 and 2. And what we want to do is revolve it around the y-axis, and this is the y-axis here. So here's the axis of revolution here. And so what we need to do is reflect it across the y-axis so you can see this thing in 3 dimensions. I'm going to do that here and change color. So the region in yellow here has been reflected across the y-axis because we're going to revolve that around there. It helps you see it in 3D. So, and now let's draw a representative cross-section here and approach it with the method of shells. Okay, and so we have a representative shell there, or a cylinder, or we can say cylindrical shell. And what we need to do is define the height and the radius, and so we can solve this problem. Because what we need to do to find the washer volume, okay, that involves multiplying the circumference, all right, times the height, all right, times the thickness. Okay, in other words, we're going to take 2 pi r times h times the thickness, which in this case is going to be delta x. Here's the thickness right here. It's the difference in x values. That's going to be a dx. Okay? So we want to write all functions in respect to x because we're going to write our integral in respect to x. So the height here, h, is going to be equal to this y value. It's a vertical distance here, and y at this point right here is equal to x. So let me define that here. H is actually equal to y, but what's y equal to on this function here, on this line? Well, it's equal to x. The radius, let me switch to blue here. The radius, r, is equal to the x coordinate on this axis here. So or you can see it this way too right here. This is going to be x, or this could be x here. Alright, so the radius is equal to x. Why? Well, because it's a distance along the x-axis. Okay? So r equals x, h equals x. Let's go for it and let's integrate. So, well, actually, let's define the washer volume first. So we get 2 pi times x, that's your circumference, times the height, which is x, dx. And that's 2 pi times x squared, and that's a washer volume. And now we need to find the exact volume. We're going to integrate from our bounds of the region. It goes from 0 to 2. So 0 to 2 of 2 pi x squared dx. This is pretty easy to function to integrate, so let's go for it. We got 2 pi times x cubed divided by 3, evaluate from 0 to 2. And that's going to be 2 pi times 8/3 here minus 0, or 2 pi times 8/3 or 16/3 pi. And if you check this out, well, in fact, let's do it on the calculator as well. We're going to understand that this right here is the function that we're integrating on. This is going to be your f of x in your calculator. All right, so let's get that going. Let's get the TI-83 here, which is synonymous with your TI-84. Okay, your TI-84 is more powerful than this, but this will work for the demonstration. We're going to go hit math. Okay, select number 9, and that's function integration. And what we need to do is enter the function in, which is 2 pi x squared. So 2 times pi times x squared. Alright, now we go comma, type in the variable that's used. In this case it's x, and it's always going to be x on this calculator. Whether we're integrating in respect to y or x, our variable on the calculator here we're going to use is x, comma, and then we're going to enter our bounds from a to b. Now a is 0 and b is 2, so I enter in the bounds from 0 and then 2, and then I hit go. Alright, and I get 16.755. 16.755. And notice that's up here. You can check that out. You can take the calculator, and you should do this. After you get your exact answer, you should take 16 times pi, alright, divided by 3, and you'll notice you get the same answer. So get your exact answer through integration here, then use a calculator and check the decimal equivalents, okay? These are the same, and that's good, and that shows you did it right. Okay? So let's do some more, because that's only 1 of 19, and let's try it again. And again, you can change your axes at any time you want. This one I'm going to really change it. I'm going to call this 1/2 and this 1 here, and this is 2 up here, and really expand it so we can see what's going on. So this is 1 here, this is 1.5, and that's 2. So I'm changing the axes there. Change the scale, that is. Okay? So change scale on axis, that's what I meant to say. Okay, so let's graph this function here. The slopes here is -1, and the y-intercept here, and the slope's -1. So it starts here, down 1, right 1. Okay, and let's graph the function. Oh, I did it in red again. Let me change that, okay? We go to black here. Let me graph the linear function first. Alright, and then let's graph y equals 0. That's the x-axis. Let's graph x equals 0. That's the y-axis. Alright, so here, let's write down the functions. This is x equals 0. This is y equals 0. And this right here is y equals x, 1 minus x. Let me change that. Going too fast. Okay, 1 minus x. And the bounded region for all the 3 of those functions is right here. And it's obviously bounded from 0 to 1. Alright, and let's revolve it around the y-axis here. There's our axis of revolution, and the y-axis. And because of that, what's going to happen is if you reflect it across the y-axis here, you're going to have the bounded region over here on the left side of the y-axis. Alright, and when you can approach this with disk too, by the way, so check your answer with the disk method. You're going to slice it, well, with this you'd slice it horizontally, but with the shells you're going to slice it vertically, you know, perpendicular to the x-axis here. And then you're going to reflect it so you can see a shell. Okay, there's a shell right there in red. So what we need to do is figure out the height, and we need to figure out the radius. Okay, now the radius is some distance on the x-axis, x. right here, and that changes as the shell increases in radius right here. The height is given by the function y, but what's y equal to? Well, it's 1 minus x. Okay. The thickness right here, the thickness is dx. So I'm going to write my integral in terms of x. So the first thing I do is I write my washer volume. Okay, remember it's circumference 2 pi r times height times thickness, which in this case is dx. And so it's going to be 2 pi times the radius x times the height 1 minus x times your thickness dx, and that'll give you the washer volume. And before we integrate, let's clean this up a little bit. We got 2 pi times x minus x squared dx. Okay, all I did was distribute through. So simplify a little bit first. Okay, and now let's find our volume. The volume is going to be integral from the left bound to the right bound of the region. So from a equals 0 to b equals 1, and so it's 0 to 1, of 2 pi, and of course you can bring that outside the integral, which most people do, minus, or times the integral of, or times the quantity, excuse me, of x minus x squared dx. That's pretty easy to integrate, so we're going to go for it here instead of using the calculator. We're going to take x squared, or excuse me, 2 pi. Let me start over here, going too fast. 2 pi times x squared divided by 2 minus x cubed divided by 3 from 0 to 1. So we're going to have 2 pi times 1/2 when we substitute the 1 in, minus 1/3 minus 0. That function right there is equal to 0 when you evaluate it at 0. So what do we get? We get 2 pi minus 3 minus 2 is 1 divided by 6, 1/6. And then 2/6 is 1/3, so you get pi thirds here. And when you get to the calculator, we're going to integrate now. I'm going to clear this out. We're going to go math, and we're going to hit number 9, or you can just use the down arrow to number 9. Enter your function in, which is 2 pi, all right, times the quantity, x minus x squared. Let's see if I did that right. Okay, comma, you put down the variable of choice, which is x, and then put in your bounds, a comma b, and we're going to integrate from 0 to 1. All right, so 0 comma 1, and then hit the go button. And we get 1.047. So 1.047, which corresponds to our answer up here. So we're looking good, but let's check to see if it's equal to pi thirds. Well, okay, well, let's take pi, that's easy to check, divided by 3, and you hit go, and notice this is the same right here. All right, so, and because they're the same, and we checked it on the answers I gave you, and this is the solution right here, and I also checked it with the calculator, we're looking good. Okay? All right, very good. All right, let's get some more practice here on number 3. Let's change the scale again just so that we can blow things up. This is 1, 2, 3, 4. 1, 2, 3, and 4. X-axis, Y-axis here. We're going to revolve around the X-axis, so we're going to be revolving this way. First thing we do is we bound the region here, given by the functions. The first function is y equals x. Slope of 1 going through the origin. Right about there. Second function, y equals 0. That's your x-axis here. And third function, y equal, or x, let me change that. X equals 2. And that's vertical line through 2. Okay. So let's label these functions here. This is y equals 0, x equals 2, and y equals x. Okay, and the bounded region is right here, this triangle right here in yellow. And we're going to revolve around the x-axis here. So let's reflect it over the x-axis here just so you can see it. That's not perfect there, but you get the idea. And let's shade that reflection in here in blue. And then let's show, so this is going to be a cone actually, because we're going to be revolving around here. So it's going to be looking like this here. It's going to be a cone. Alright, now we're not going to approach it using discs with vertical cross sections here. We're going to approach it with shells. So the first thing we do is we draw a rectangular cross section and we reflect it right here so we can see the shell form. Okay, that is a shell. Alright, now you can solve this problem with other methods like the this method, but we're going to solve it with the shell method. Alright, and what we want to do is find the volume of the shell first. Alright, shell volume. And remember, that's 2 pi r times h times your thickness, which in this case, thickness right here is dy. Alright, so it's going to be dy times the thickness. So I need to write all my functions in respect to y now. Keep that in mind. Okay, so what we have to do is define the radius and the height before we find the shell volume. Okay, so let's start with the radius here. The radius is here. That little distance there, radius, and notice it's a y value. So r equals y. Okay, the radius is here. Excuse me, let me just put right here, r. Okay, that's the radius. And then what is that equal to? Well, it's a y value. Okay, so r equals y. That's the radius. And now we need to find the height. Okay, and the height is the distance between the bases. That's seen this way. That's h. Okay, well, what is h? Let's find that out. Okay, now h is exactly this distance here. So what we have to do is to find the distance here first. This distance, which is equivalent to this distance here, so either one. Okay, now that's some distance along the x-axis, so I'm going to call that x. And what we do for horizontal distance is we always figure out the horizontal distance using right minus left. So h is equal found by taking right minus left, and that right point here is obviously at 2 because we're on the vertical line at x equals 2, minus the left, okay, which is obviously x. So 2 minus x. But like I said earlier over here, it's a dy problem, so we're going to have to write everything in terms of y. Well, I know x equals y, so the height is equal to 2 minus y. I just make a substitution. So I know my radius is y, because it's a y value there. I know my height, I can go for the shell volume. So it's 2 pi times y times the height, which is 2 minus y, times dy. Simplify. I get 2 pi is equal to, and distribute through the 2, or the y here, I get 2y minus y squared times dy. And there's my shell volume. And I just have to figure out the limits of integration. And the shells are formed, and the lowest shell is formed at 0 all the way up to this point here. And that's b, that's my upper bound, where a equals 0 is my lower bound. Again, the bounds are seen vertically here. Alright, so I need to find the volume, I need to integrate from 0 to 2 in this case. Alright, and then I'm going to integrate my my shell volume, because what the integral does is it adds up the infinitely thin shells. So I take 2 pi times the quantity 2y minus y squared dy. You can obviously pull that 2 pi out. So let's do that. Actually, 2 pi times the integral of 2y, or the antiderivative of 2y, which is y squared, minus y squared, y cubed divided by 3, all evaluated from 0 to 2. What's that? Well, that's 2 pi times 4 minus 8 thirds, minus 0, of course, when you evaluate that function at 0. What do we get? Well, we get 4 minus 8 thirds, which is 4 minus 2 and 2 thirds, which is 2 pi times 1 and 1 third, or 4 thirds. 4 thirds times 2 pi, and that's 8 pi thirds. Well, what is that as an approximate decimal? Let's figure that out. Well, let's actually consider this. This is our function right here. This is our f of x. Whoops, f of x here. Alright, I'm going to enter that in the calculator and evaluate it using the calculator, because we need experience on that, because you're going to be using that in the future more and more. Alright, because the tests are written that way. So, what I do is I go math, okay? You can either go down to number 9, like this, okay, and take function integration, or when you're in the beginning here, just hit number 9. Boom, you're done. And then you enter the function in, which is 2 pi, so 2 pi times the 2y. Well, the calculator is going to put in x, but don't worry about it. Just assume your variable is x. Okay? So 2x minus x squared Alright, put in the variable that you're using, x, put in the bounds a to b, so 0 to 2 in this case. Alright, and then hit the go button. And you get about 8.377, which is, or 5, which is 8.378. So 8.378, which corresponds to our solution here upstairs. Okay, so these are the same. One's exact, one's approximate. Well, you know what? That brings us up to the point. How do you know they're the same? Well, let's find that out. Let's take 8 times pi divided by 3. Okay? And that's the same thing. So you know you did it right. Okay, so get happy. And hey, you're learning the shell method. Alright, let's try another one in just a minute. Okay, on this other one here, let's also change the scale again, because I'm just like expanding it so you can see a little bit better. That's the only reason why I'm doing this here, because the scale's too small. Let's graph this now. This is b, and m is -1 and b is 2. So it intersects at 2 with a slope of -1. Alright, so it looks like this. Let's grab a line tool and graph that big boy. Alright, so here's our function y equals 2 minus x. Y equals 0 is here, the x-axis. X equals 0 is the y-axis. And we bound the region. Alright, right in here from 0 to 2. Let's label the axes though. So this is x equals 0, y equals 0, and y equals 2 minus x. Now we're going to revolve it around the x-axis, and here it is. So here's our axis of revolution right here, and because of that, if I want to sketch the image or the solid here, I got to reflect it across the axis so I can, try to look at this thing in 3 dimensions here. So let's give that a shot. Now, this is going to be a cone facing to the right. Alright, you're going to see it like that. And you can approach this using vertical disc, no problem. Alright, but let's not do that. Let's get practice on the shell method, and then you can do the disc method with vertical cross sections later. Okay, so here we go. I'm going to draw a representative cross section here. I'm going to reflect that cross section over here so you can see one of the shells, one of the infinite number of shells. And I'm going to start labeling here. Okay, this distance here is the radius, and it's a y value. This distance here is some y value. Don't know what it is, but it's equal to, well, if you want to figure out what it is, it depends on x, doesn't it? 2 minus x. What's a y value? The height is seen here, and that's h. And the thickness is going to be a difference in y values here, because it's a horizontal cylinder, or cylindrical shell. Okay, so what I need to do is figure out the height. And the height right here is an x value. Height's given by x. This is a horizontal distance, x. Well, what's x equal to? I don't know. You got to solve for x here. So let's do that. Let's take that and let's solve for x. Actually, let's do it down here. So I've got y equals 2 minus x, and after you add x and subtract y, you get x is equal to 2 minus y. And so that's going to be equal to 2 minus y. Whoops, I didn't write that correctly. Let me change that. Okay, and remember, on a dy problem, you're going to have to write all your integrals or all your functions in respect to y. Remember that. And to do that, you got to solve your functions for x. You got to solve for x and write it in terms of y. That's why I did this here. Alright, now let's get our shell volume. Okay, that's equal to 2 pi r, the circumference, times the height, h, times your thickness. In this case, thickness is dy. Okay, so we got 2 pi times r, which is y, because it's vertical this time, times the height, which is 2 minus y, times your thickness dy. Let's simplify that and let's distribute through the y. So I get 2 pi times 2y minus y squared times your thickness dy. And there's your shell volume right there. And then now you want to integrate. How do you integrate? Well, you look at your bounds. Okay, your bounds are from 0 to 2. So a equals 0 right up here. B equals 2. Those are your bounds seen vertically. So let's see, integrate from 0 to 2 of our shell volume. So 2 pi times 2y minus y squared dy. Okay, well, what's that? Well, it's 2 pi times y squared minus y cubed divided by 3, evaluated from 0 to 2. Sorry. What's that? Well, let's take 2 pi times y cubed divided by, excuse me, start over. Going too fast, I got to substitute in 2. These are constant now. 2 squared is 4 minus 8/3. And then when you evaluate this whole thing as 0, you get 0. Well, that sure sounds like the previous problem. So this is 2 pi times 4 minus 2 2/3, which is 1 1/3 or 4/3. So this 2 pi times 4/3, and that's going to be equal to 8 pi/3, which is the same as the previous problem. It's going to be approximately equal to 8.378. Now let's make sure we got that, okay? It's a new problem, so let's verify that on the calculator. Okay. Now, first thing I do is understand that this is my function f of x. That's what you enter in the calculator. Okay, so let's try that. Whoops, that's the wrong one. Hit math, hit number 9. That's a quick way to get the function integration. All right, enter my function 2 pi. All right, times the quantity 2y, or 2x in this case, times the quantity, excuse me. Yeah. Nope. I got to go back. Got to look closely. 2x minus x squared. Again, even though your function is in terms of y, when you enter in the calculator, just assume x is the same as y, and you just input the same thing, but in respect to x. Okay, and let's square that guy. Enter in our variable. Enter in our bounds 0 to 2. So 0, 2, and then hit the go button. Alright, and notice it's the same thing, but how do you know that? Well, 8 times pi divided by 3 is the same thing. Okay? So just keep that in mind. Alright, and that's how you do the first 4 problems. So let's do a couple more. I'm going to pause it right now and get it all set up. 5/2, 2/5. Thirty-two, 2 to the 5th, 32, 100, 129, 5/5. Okay, let's try this again because I obviously made a little mistake here, so on the recording issues. So I'm going to go into graph this function one more time. And let's see here. We want to take y equals root x, y equals 0, and x equals 4 and bound that region and then revolve it around the y-axis here. Okay, and we're going to revolve it around this axis here. And let me change the scale just a little bit here so we can blow things up. This is 1, 2, 3, 4. 1, 2, 3, 4. I keep saying that you can change the scale because I just put a general graph in here just so that you can have one to graph. Let's graph y equals root x here. When x is 0, root 0 is 0. When x is 1, root 1 is 1. When x is 4, root 4 is 2. So we graph root x as so. Okay. Now you're going to graph y equals 0. And y equals 0 is the x-axis. And x equals 4 is over here. It's a vertical line of 4. Let's label those functions there. So that's x equals 4 vertical line, y equals 0 is a horizontal line, and the bounded region is right here in yellow. All right, the region bounded by those three functions. Now, in order to graph the solid in 3 dimensions, you're going to have to revolve it around the y-axis here. And to do that, you're going to have to reflect 4, 2 to 4, negative 2 here. 1, 2, 3, and there's negative 4. And then reflect 1, 1 to 1, negative 1, 1. So, no. Okay, there we go. And then you're going to have to graph or reflect x equals 4 over here to x equals negative 4, and then graph or shade in the bounded region in blue here. That's going to help you take a look at a solid in 3 dimensions. Now, when you revolve this around an axis, it looks like a cylinder with a curved inside. It's got a hole in it. All right. Because of that, you can approach it using washers, but let's not do that. Let's approach it using shells. So let's take a cross section here, reflect it, so we can see the other one, and draw a typical shell. Okay, that is a shell. So we need a shell volume, of course. So let's work on that. We need to define the height right here. The height is some y value. It's some y value. In this case, it's equal to, well, whatever this y value is. And hey, the y value is root x. So the height is root x. Okay, we need to find the radius too. This position on the x-axis is x here, so the radius is x. Some distance along the x-axis, going from 0 to 4, and it's changing. 0 all the way to 4. So once I define the radius and the height, I can find the shell volume. So here we go. Here's the volume of a typical shell. You take the circumference, which is 2 pi r, or in this case 2 pi x, times the height, which is root x, times your thickness, which is dx. Your thickness is right here, dx. It's differential in x values. Now root x is 1/2 power. X times x to the 1/2 power is x to the 3/2 power. So when you simplify this, you get 2 pi times x to the 3/2 dx. And you want to do that before you integrate. Okay? Now the bounds of integration are from here to here. These are the bounds. Alright? A equals 0 here, and obviously B equals 4 here. So when we find the volume, we want to integrate from 0 to 4 of 2 pi times x to the 3/2 dx. This is a pretty simple one to integrate. So what we'll do is we'll take 2 pi times, 2/5 times x to the 5/2. And we're going to evaluate that from 0 to 4. 2 times 2/5 is 4/5, so we get 4/5 pi times, the square root of 4 is 2, 2 to the 5th is 32. So 4 times 32 is 128, so you get 128 pi fifths. And that's approximately equal to, I don't know, let's figure that out. Now keep in mind that this is your function here. This is your f of x. So when you do this on the calculator, that's what you're going to enter. Let's see if we can do this correctly here. So we're going to have, let's turn the baby on, clear it out, hit math, hit number 9, get your function integration, enter in 2 pi, alright, times x to the 3/2 power. So x to the power of, and you're going to have to put your power in as 3 divided by 2 and make sure that it's in, oops, got to change that, in parentheses. Your power must be in parentheses. Okay, now let's state the variable, and let's state the bounds. It's from 0 to 4, and let's hit the go button here, and hopefully we get this right. We're looking for 80.425. My 83 is a old calculator, so it takes a while. Your 84 plus is going to go do it much faster, or 8099. And notice that our answer here, 80.425, is the same as the given one. Okay, so here, whoops, we're gonna, here's our answer. Let's state it here. So it's approximately equal to 80.425. Okay, these are the same. One's exact and one's approximate. Okay, let's do one more before we end the part 1 on the video here, just to get some more experience. When I explained the washer, the shell method here in the first day, I assigned problems 1 through 10. I'm going to do 1 through 6 here, and then I'll do 7 through 10 later. And then day 2, when we get back, we'll talk about it, and then you can do the next 9 problems, okay, to gain some experience. And once again, you should be doing these with the disc method too, or the washer method, to verify your results and gain extra practice. Okay, so remember that. Okay, I'm not going to change the scale here. Because I noticed that this parabola has a vertex at 0, 4. I need some room to graph this thing. Okay, when x is 1, you get y equals 5. Let's see here, when y equals 5, so when x is 1, y equals 5. And when x equals 2, this is 2 right here, 2, 4, 6, 2, 4, 6, 8, 10. When x equals 2, 2 squared is 4, 4 squared is 8. I should have probably changed the, well, that's fine. Okay, and then you plot 2, 8, which is right here. So let's graph this function. Let's reflect it first, and then so we can graph it. Okay, and there's x squared plus 4. Okay, now we want to graph y equals 8. Well, y equals 8 is a horizontal line at 8 right here, and that's y equals 8. And we want to bound that region. Well, it's right in through here. Whoops, I forgot. X is greater than or equals 0, so let me change that. Since x is greater than 0, you're in quadrant 1 only. This is quadrant 1 or 4, but since we're above the x-axis, it's got to be in through here. So let me bound the region here. X is greater than or equals 0, so you're on the right half. Okay, now we're going to revolve around the y-axis, and the y-axis is right here, and this is the axis of revolution. This y-axis right here. And so what it's going to look like is well, it's going to look like a part of a paraboloid, actually. It's going to be round and pointed at the vertex here at 0, 4. All right, now we can approach this using a disc with a horizontal cross sections. It'd be really easy to solve, but you can check it with the disc method. Check with disc. Okay, but let's do it with shells. All right, now what I'm going to do is do a vertical cross section. I'm going to reflect it, and I'm going to draw a typical shell. Okay, what we need to do is figure out the height, all right, h, and we need to figure out the radius, r. And the radius is right here. And it's some x value. That is the radius right there. Okay, so the radius equals r. The height, well, what's that equal to? Well, let's see, it's upper minus lower. So upper minus lower. Yeah, the height here is 8, and the lower function is x squared plus 4 because you're on the parabola here. So it's 8 minus x squared plus 4. And when you simplify the height, you get 8 minus 4 minus x squared, which is 4 minus x squared. Okay, now why do I want to do that? Well, I noticed that the height, or excuse me, the thickness is dx. And because of that, I need to express all my functions in respect to x. Okay, so let's get a shell volume now of 2 pi times the radius, which is, again, the radius right here is x. So you're going to have 2 pi x, which is the circumference, times the height, which is 4 minus x squared, times your thickness, which is dx. Well, that simplifies to 2 pi times 4x minus x cubed dx. Again, I just want to distribute right here and simplify it. Now the bounds of integration are the bounds of the region, and the bounds of the region are found by taking the functions and intersecting them. So let's find the intersection points, and it's pretty obvious it's from 0 to 2 here. But, you know, hey, let's just prove that. So I'm going to substitute 8 in for y, and I have to solve 8 is equal to x squared plus 4. And that means I get 4 equals x squared, and that means I get plus or minus 2 equals x. And so my left bound is a equals 0, and my right bound b equals 4. This is the bounds of integration. Okay? Bounds, 0 to 2. Look at the yellow region, the bounded region is from 0 to 2. So my exact volume is going to be found by taking the integral from 0 to 2 of 2 pi times 4x minus x cubed dx. And that's going to be equal to 2 pi times, let me change that, the integral of 4x is 2x squared, or the antiderivative, minus x to the fourth divided by 4, evaluated from 0 to 2. And that's going to be 2 pi times 2 squared 4 times 2 is 8, minus 16 divided by 4 is 4. Alright, and that's 4 times 2 pi, or 8 pi. Okay, now 8 pi is going to be equal to 8 times 3.14, 159, so on. Alright, and that's going to be about 25.13. Excuse me, 133. Let's verify that. Let's go to the calculator here. But before we do, understand that our function is right here. This is your f of x. Alright, we're going to enter that into the calculator, and we're going to take, well, first of all, we better turn it on. And then next we hit math, number 9. Alright, enter in our function at 2 pi. Alright, times the quantity 4. Whoops, that's an incorrect keystroke. 4x minus x cubed minus x to the third power. Where's 3? There you go. Close it off. Enter in our variable, which is x. Alright, enter in the bounds, so 0 to 2. Alright, and you hit the go button. And notice you get the same value, 25.133. Okay, so understand that these are the same. Alright, and we check by calculator. Check by calculator. Alright. Alright, and that's the last one in this part 1. So I'm going to stop the recording here. If you want more problems from 7 on through 10, you can go to part 2.